Hello class and welcome. In this video, I'm going to explain the first parts, day one of our notes for 5.3 polynomial functions and their graph. The learning objective in this video is to explain how to determine the degree of the polynomial function given in standard form, in its factorization form, and also if we have a graph of the polynomial. Let's begin by first identifying what the definition and the standard way of writing a polynomial function. Assuming that n is going to be a non-negative integer, so any positive whole number, and a sub n minus 1, and so on are going to be real numbers, where the leading one, a sub n, doesn't equal to 0, then the polynomial function is defined by the following format. F of x equals a sub n times x to the power of n plus a sub n minus 1 times x to the power of n minus 1. And we keep on adding those terms until we end up with the following two terms. A sub 1, well, the following three terms. Let me make it a little bit smaller. A sub 2, x to the second power, a sub 1 times x, and then plus our constant. So let me just move this over a little bit so I could fit it all, and there we have it, okay? So this would be the notation for this. So all we're doing is essentially just getting a power function and then adding those power functions again throughout the entire, um, adding again a bunch of power functions until we end up with the quadratic term, the linear term, and our constant at the very end. Now this again is referred to as a polynomial. That has a degree of n units. So this number here normally should be the largest one, but that would represent the degree of the polynomial. And the number a sub n, that's referred to as the coefficient of the variable to the highest degree, and that's referred to as the leading coefficient because it's in the front. Now the domain of these polynomial functions is all real numbers, because again you're going to end up with, as you see in the graph, a graph that extends from negative to positive infinity, curving up and down in that domain. Now, how do we determine the degree of the polynomial? Well, like I stated, it's just simply identifying what the largest exponent is. Now, what's in standard form, that term should always be in the front. Now, if we only have one term, well, that makes it simple, because when you have one term, the degree of this thing would be this exponent there. So this polynomial is a polynomial of degree 6. While on the letter B, since there is no x to a power, that means that this is a polynomial of degree 0, your constant. It has no x value, so the degree is 0 for that term. Now, if you look at letter C we do have it in standard form, x to the fifth, x to the second, and x to the 0 power. They don't have to be, again, consecutive numbers. It could be terms, again, where our x to the fourth has a coefficient of 0, our x to the third also has a coefficient of 0, and that's why we don't list them again and add them to these values there, because the coefficients are 0, so we omit them again from the actual equation. So in this example, since 5 is the biggest exponent, the degree of this polynomial would be 5. And the degree to the next one is not going to be 4, but 8, since 8 is bigger. And that's how you determine the degree of a polynomial in standard form. Now, what about if it's in factored form? Well, since a polynomial can be written as the factors, as linear factors, there's this theorem called the linear factorization theorem that states if we have a polynomial, again, our standard way of writing a polynomial, where n is going to be bigger than or equal to 1, and again, this first term, this leading coefficient is not 0, then every polynomial can be written as the product of linear factors. And the number of factors that I multiply correlate directly to the degree of this thing. So if this is a degree 5 polynomial, then that means I can multiply 5 linear factors. So I could multiply an x minus, let's say, 1, an x minus 3, an x plus 4, an x plus 7, and an x plus 9. 1, 2, 3, 4, 5. If that degree right there was 5, we can multiply a total of 5 linear factors. So therefore, the nth degree polynomial can be expressed again as a product of any non-zero constant of n linear factors, which means that the degree of a polynomial in this factored form is simply going to be the sum of all of its linear factors, since it correlates again to the degree of the polynomial. How many of these multiply correlate again to this. Now, they don't have to be distinct. There could be a situation where a couple of them are repeating, like in this example that we see on example 2a. On example 2a, we see that we have negative 3 times x to the fourth power, which is the same thing as x minus 0 to the fourth, times x minus 2 times x plus 3. So since we have an x and we, of course, we have negative 3 right there. But the linear factors are these three values right there. So since we have 4 right here, imagine x minus 0, x minus 0, x minus 0, and another x minus 0. So we have 4 there plus 2 more. That's a total of 6 linear factors that are multiplied. Therefore, the degree of this polynomial will equal to 6. And similarly, the same thing on example 2b. The degree of this polynomial, since we have negative 7, x minus 0 to the first power, x minus 4 to the second power, and x plus 2 to the fifth power, the degree of this polynomial is 8. 5 plus 2 plus 1 is a total of 8. Now let's change gears and let's talk about how to identify the degree of a polynomial when we're given a graph of that polynomial. Well, we first have to be able to recognize that we have the graph of a polynomial because only polynomials can be classified by their degree. So let's discuss how can we tell if we're looking at the graph of a polynomial. Well, polynomial functions of degree 2 or higher are going to have graphs that are going to be smooth and, not or, and continuous. Now, what do I mean with smooth? When I use the word smooth, I will refer to the word smooth. I'm referring to the idea that my graph is not going to have any sharp corners. That anytime I'm changing direction and I'm moving from going up to going down, increasing to decrease, that turn is going to be rounded and not sharp. Now, continuous means that the graph has no breaks, no holes, no gaps, and that if you were to trace the graph from left to right, from negative to positive infinity, you should be able to trace that entire graph without having to lift your pencil at all. So if it satisfies those two conditions, then the graph that we're looking at will represent the graph of a polynomial. Now, how do we determine what the degree would be? The number of turns on the graph of the polynomial is how we determine, again, the degree of the polynomial. And it's the following: that the degree of the polynomial is at least 1 unit higher than the number of turns in that polynomial. So let's say that the polynomial changes direction, it turns twice. It goes up, goes down, and then goes back up. So it changes direction twice. That means that f, this polynomial f, is going to have at least a degree 3. So it's going to be at least, the degree of f is going to be at least 3. It could be a degree 4, it could be a degree 5. Well, more likely 5, and we'll talk about that later on. But 5, 7, but the smallest degree it would have to be at least is going to be 3 because of the 2 turns. So 2 plus 1 is 3. So let's look at some examples of this. Look at example 3a. Determine the degree of each polynomial. Well, again, first we have to be able to determine if we have a polynomial, because only polynomials can be classified as degrees. And this one is not a polynomial because of the sharp turn. So no degree. Well, letter B, the same thing, not a polynomial because of the gap here. There's a break in the graph. So yet again, no degree. And if we look at the last example, this is a polynomial function. Notice how it's continuous. I can trace over the graph with my pen without having to pick it up. And in the places where I'm changing, notice that those changes, again, are rounded. They're not sharp turns. Like in this example right here, this one is a sharp turn right there. So this is a polynomial. And because it's a polynomial, it has a degree. We can classify the degree. And the degree of this thing, because of the two turns, is going to be at least 3. So this is going to be at least x to the third power plus a bunch of other things until we get to our constants, okay? But the biggest exponent here has to be at least the number 3. It cannot be any lower than that value of 3. Now, because, like I said, polynomials are the only functions that are classified with degrees, it reminds me of a little joke here. What is the only function that graduates from the university? Your polynomial functions, because they're the only ones with degrees. I know, not that funny of a joke, but I thought I included there. Well, that includes again the first part of this section, how to identify the degree of a polynomial. I hope this video was helpful and I appreciate you watching. Have a good day and goodbye.